Okay, the pictures there mainly just to keep things in focus. I get blurry. If I don't have a picture to look at or whatever. But coincidentally, I just noticed the lighthouse and the cylinder here. There's kind of an aesthetic to this. Still, it's the cylinder I want to talk about. Okay, so got the cylinder. Then we just did this by discussion, so I'm just going to do kind of quickly, just to remind everybody. I asked if I set this thing here, and I've got water in here, and I've got this thing plugged off, and remove my finger, you would expect that water would come out here and fall to the floor. So my question is, what can we measure to predict where the water would hit? And the first thing somebody said, well, get the velocity the water comes out of here. Because if you got the velocity at which the water comes out of here, you can see what the angle is going to be, and you can do the projectile motion and figure out where the water is going to hit. Or if you know where the water is going to hit, you can figure out how fast it's going. Okay, well, we got to that pretty quickly, and that's a good way to break down the question. Okay, but then the question is, okay, how do we get the velocity of the water coming out of the tube? And I never know where these discussions are going to go. I have one way of doing it. We didn't really get to that, but we did something last time. But what we got to was, ask the question, okay, well, why does water come out of the tube? Well, that's because of pressure. Okay. Yeah. So I think the first thing was a difference in pressure between inside and out. Okay, so the pressure difference does it. How does that happen? Now, what I had in mind was, well, you got a tube with a certain length. Okay. And a certain amount of water in the tube. And the force exerted by pressure on one end of the water in the tube is greater than the force exerted on the other end, and all that stuff that we talked about last time. And we could measure the tube and figure out the mass of the water in the tube and all that stuff. But we got into the question of how do you get the pressure here? Okay, well, why is there pressure here? Well, there's water in the tube and the water's pushing down and all that stuff. Okay, so how do you get the pressure if you know that? Because this is one thing we didn't. This is one connection we didn't make last time because we ran out of time. So what's the pressure at this point due to, say, this much water? Okay, well, we can measure this. We can measure the area across, we can measure the diameter of the tube and figure out the cross-sectional area. So we can figure out the volume and multiply that by the density of the water. And we got to that fairly quickly, okay? Just trying to find the right words. But how does that give us pressure? Well, actually, this is in response to the question I asked, how much force does it take to support this water? Okay, well, it's the weight of the water, and then you get the weight by measuring the distance, the density of water, measure the diameter, you get the volume, and you can figure out the weight of the water. Then I asked, well, how does the water down here support the water up here? And it's not totally obvious, but it's the pressure. It's the pressure down here that supports the water up here. So if we know the weight of the water up here, we get the pressure down here. How do we get the pressure down here? And if you're not here, if you probably stop every time I ask a question and think about the answer. Well, to get the pressure down here, we divide the force exerted by the water down here by the cross-sectional area, because it's the pressure down here that holds up the water above it. And all that leads to back to the original picture of this situation. But water flowing out here. If this distance is h, so we're depth h here, then we have the cross-sectional area A sub CYL, area of the cylinder, cross-sectional area of the cylinder. And we got H. It's H times the area of the cylinder. Let me just put the right row down here. Get a little bit. Rho, G, H. G, but I think that's legal. Density of water times acceleration of gravity times H. Depth times the area of the cylinder. So from down here, I leave myself a lot of room, but pressure exerts this much force. Pressure is force per unit area. So it's a uniform cylinder, so there we have it. Okay. Turns out that's just rho GH. Now, if we put that together with everything we did last time, we can write Bernoulli's equation. I don't think I did this last time. But rho GH plus 1/2 rho V squared plus P is constant. It's just like MGH plus, I got P. I have to put that in the middle, so I have to erase the whole thing to write it correctly. Well, I'm just doing this by analogy. There's deeper connections we can make, and we probably will when we do this in the lab. Okay. But how's rho GH related to MGH? Well, rho is just your density, right? Which is your mass per unit volume. So rho is M over V. So if I multiply everything in this equation by V, by a volume, I get mgh, and I get 1/2 mv squared, don't I? Now, I haven't said where I'm taking the mass of, it'd be some incremental fluid, but, just again, by analogy, if I multiply this by V and multiply this by V, that's what I get for any increment of fluid, okay? And then we have pressure times volume, okay? Well, pressure times volume has units of energy, because pressure is force per unit of area. Volume is volume. If you divide volume by area, you get a length. So it's a force times a length. And we're going to do quite a bit with that. We might even talk about it a little bit more today. For right now, we're just going to kind of see that this is analogous to this, and then we'll kind of bring out the reasons for some of these analogies. I'm not sure if you've got the whole board in the picture. Okay. Well, we can apply Bernoulli's equation to this situation. Okay. If we compare this expression at two different points. Okay, so let me just draw this picture again. Okay. This will be point A. This will be point B. And here's point C. A is at the surface, B is down here at the level of the hole, and C is this point at the level of the hole where the water's coming out. Okay? Now, from A to B, what's constant? Now, you have 4 possible variables here, because this applies to any fluid, including air and gases. Okay, rho density can change in air. So if you have an airflow, chances are you have pressure changes, which give you density changes. Okay, that makes things more complicated than what we can deal with in this course. Although you have the differential equation skills, we could deal with it. We're not going to take the time because it's fairly complicated. Okay, so you're in a position that if you have to analyze things with variable rho, you could do it. You could at least write the differential equations. You might not be able to solve them because they can be pretty nasty, depending on the situation. You can at least put them into a solver. Okay. And preferably you could solve them yourself because you gain insights by understanding the solution sometimes. Okay, so rho is a variable, but we're going to treat it as constant because we're just going to talk about incompressible fluids in this course. That leaves what as variables, okay? Now let's just discuss it quickly. Okay, so it's very obvious what the 3 variables are, everybody understands. We said V and H, I realized, okay, I'm using H over here. But generally, I prefer to use the Y coordinate. You both might use H. Y is a little more general. Doesn't really make a lot of difference, but I'm going to use Y. Maybe it's a prejudice because I really hate the formula mgh, which obscures what happens when gravity is changing. Okay, and people always get hung up on that because of that stupid formula. It's potential energy is equal and opposite to the work done by the gravitational force. Period. Gravitational force is constant, yeah, you get mgh. If it isn't, you get something else. You gotta get it. Okay, well, you know that. Okay, so I'm gonna say your variables, if we assume rho is constant, which means the fluid is incompressible. It turns out that even water is not really incompressible, but most liquids are pretty much incompressible. My high school physics teacher told me water is absolutely incompressible. He worked in hydraulics a lot. He had two jobs. He's an excellent physics, chemistry teacher. He was outstanding. But he had this idea that water was incompressible. So one of the few things he told us was that water is absolutely incompressible. I kind of questioned that, but he was a big violent guy. I didn't want to put a question on it. For practical purposes, that the pressures that we deal with, even with hydraulics, it can be treated as incompressible. It's not absolutely so. Nothing really is. There's nothing macroscopic. Okay. So assuming rho is constant, we're incompressible. Then y, b, and p are the variables. What varies between point A and point B? Okay, first answer I got was all three change from A to B. It depends on how close point B is to the hole. If the hole is small, by small hole, we mean as small as we need to make it to make what we say true. From A to any point here that's not real close to the hole, there's no change in velocity. Okay. If you got a bigger hole, then there definitely is, and we're going to deal with that. So from A to B, velocity is constant. From A to C, what doesn't change? Is it Y, is it B, or is it P? Well, what do you think? Well, at A, the surface is exposed to the atmosphere, so it's at atmospheric pressure. And the water stream is exposed to the atmosphere, so it's at atmospheric pressure. If you're exposed to the atmosphere, then you're either at atmospheric pressure or very quickly become atmospheric pressure. Now, for a macroscopic body under pressure, it might take a while to expand, but water doesn't even expand. So we're going to say pressure is constant. Technically, for a very short distance out here, you'd probably say that water still adjusting the pressure to the pressure. Okay, from B to C, what is it that doesn't change? Okay, it's fairly obvious. There aren't any real caveats here. From B to C, B is at the level of the hole, the water's coming out at the level of the hole, C is at the level of the hole. So is B, so that Y is constant. Okay, so from A to B, here's a rho GY1 plus P1 equals rho GY2 plus P2, because this whole thing has to be constant. And B isn't changing, so this is just automatically constant. Only these two can vary. Okay. What happens is you go deeper to the okay. How does pressure change when you go deep? Well, you know that it increases, right? Well, if you go deeper, what happens to Y? You know Y decreases the deeper, you default them upward being a positive direction, Y decreases. And if Y decreases and all this remains constant, and this isn't changing, then pressure better increase. Okay, if something's constant, sum of two numbers is constant, and you decrease one of the numbers, you have to increase the other, right? So you've got to use those ideas. They're not deep ideas, but it's kind of deep to apply them to this situation. Okay, well, this can then be written rho gy plus delta p equals 0. Yeah, just subtract rho gy one from rho gy two. You get rho g times y2 minus y1, right? Which is rho g times delta y. If you subtract P1 from P2, you get P2 minus P1, which is your delta P. And if you subtract this side from this side, that's what you have, and you're left with 0 on this side, so that has to be equal to 0. All right. So can you write out a similar set of equations, two equations, an equation like this and an equation like this from A to C? Absolutely. Okay, so what you got? This one is just what happens when B is constant, and you get what I said here. If you write it out, the equation where P is constant, then the P doesn't have to be written. The change in P is going to be 0. You just have the changes in rho gy and 1/2 rho v squared. The change in rho gy is just rho g times the change in y, because rho and g are constant and don't affect the change. And the 1/2 rho v squared changes, and it's v squared that changes, not v. So there's always a tendency to write, we do, okay. You're gonna write out rho g delta y. You do do the intermediate step. You want to write this step out so you know what this step means. And you're going to get a rho g delta y. What you're going to get is a 1/2 rho times the change in v squared, delta of v squared, not delta v squared, which could mean v, squaring the delta v. Okay, with no parentheses. It could be interpreted that the parentheses are here, parentheses around the whole thing, and that is a huge error in many cases. Okay, down here, if y is constant, then it's v and p they're changing, and you get this. Now, this means that if you have constant pressure, if y changes, then v has to change. If y decreases, then v has to increase. If y increases, then v decreases. Okay. What's the examples? It's tempted to do one there. And similarly, if y is constant, then any decrease in v is going to be associated with an increase in p. And any increase in v is going to be associated with a decrease in p, and so forth. So you want to get that intuition. These things, when one variable is constant, the other two change in opposite directions. Now, that's great, but how good does that mean? Well, let's just go back to this one. Okay. between A and C, P is constant. What happens to Y? Up or down? What happens to V? Has to go up, does it? Well, this is slower than this, unless this hole is really big or something, okay? Well, it's still gonna be a little slower. Okay, if it's a small hole, then this is much, much slower than this, and the velocity of the fluid up here becomes insignificant, especially since you're squaring it. We'll work out some examples to see. Okay. Now, between B and C, pressure changes, velocity changes. Okay. Inside here, the fluid is, it's a small hole, the fluid is pretty much stationary. Outside, it's split out. So what happens? What changes? Okay, well, V changes. V increases. What's the other thing that varies? Pressure. Pressure has to then decrease. And of course, that was kind of our first intuition. It's what we did last time. And when we discussed things at the beginning, everybody understood it was the pressure difference, pressure decrease causes the water to come out. Okay. So there are ways you can see this. You can see that since this is moving and this isn't, then the pressure must be decreasing. Okay. Now let me say something that I haven't really said. This all applies to a continuous fluid. If there are any breaks in the fluid, then what happens in this part of the fluid is kind of independent of what happens in this part of the fluid. Any changes that happen over here once the fluid is broken doesn't influence the changes of the chunk of fluid that's over here. But we have continuous fluid from here all the way here. Okay. All right. Okay, well then, you know, from A to B, what happens to Y? Decreases. What's the other thing that varies? Well, velocity doesn't, so it's pressure, and pressure has to increase. Okay. You want to think that way, think in terms of 2 points and what happens. Now, let's say you have a house. The wind is blowing hard. So you got wind. Wind comes in here and blows over the house. In encountering the house, well, the wind here is moving fast. The air is moving fast. How fast is the air moving inside the house? Yeah, it might be moving a little bit if you got the windows open, but it's not moving much. Okay, as long as the house is intact. So point A is here and point B is here. Now the density of air is about 1,000th, about 1/700th. Let's say one, yeah. Between 70 and 80%, point between 700. Never mind. I don't even know what I'm saying. 1/700th. 1/800th. Was it 1/800th of the density of air? It's approximately 1.3 kilograms per cubic meter as opposed to 1,000 kilograms per cubic meter. Okay. Between A and B, and let's say A is just inside the roof and B is just outside the roof. Rho GY isn't really constant. Y changes. But rho is really small. So rho GY becomes more or less a negligible term for the 8 inches you have between your sheetrock and your shingles. Okay. Rho GY is a small number. You can work out the number and compare that with atmospheric pressure. Okay. Incidentally, atmospheric pressure is about 100,000 newtons per square meter. If you've read the chapter, you know that. You only have 2 days to read the chapter. You need to read it if you haven't. And you should at least scan it. Um. So essentially, Y is constant, which means where V is bigger, what is P? P is smaller, right? So where's the pressure greater, point A or point B? Here, pointing up, pointed. Okay, I forgot to start pointing. Okay, well, what I've labeled here is that rho gy is very small, so there's more velocity at B, meaning there's more pressure at A. Which means then you take the pressure difference and multiply by the area of the roof, and you know how badly the wind wants the roof to leave your house. And if the wind is really fast, like in a hurricane or tornado, very common, the roof is pulled off. And you get hurt if you're inside, but a lot of times the roof, then the wind just catches the roof and goes away. People end up unscathed. And let's hope that happens to you. That's the worst that happens. Okay. Now let's consider the wing of an airplane. Okay. The wing of an airplane is shaped so that air flows faster over the top than over the bottom because the bottom kind of catches it a little bit. And you got ailerons, you know, lower these things and really slow it down, right? Okay. If you know about a little bit about airplanes. So pressure is greater below. So you multiply pressure difference between here and here, here and here, by the area of the wing, and you get the lift. We get to stay airborne. Okay. Question is, how do people fly airplanes upside down? And that kind of gets reversed. Oh, you also can angle your wings so the impulse momentum is greater than the Bernoulli effect. Impulse momentum, the momentum of the air is getting changed in this direction, which tends to change the momentum of the plane in this direction. It's kind of tricky flying an airplane upside down. I understand. I've never flown anything. Okay, that makes sense. Just typical cases. And all you got to do is crunch the numbers. If you know the velocity here and the velocity here, it's easy to calculate the pressure difference. I mean, one of these, this one, that one. Okay. Oh, okay, well, here it is. Here it is. No, here it is. Okay. If you know two pressures, or you know the two velocities and the difference in pressure, you can get the difference in pressure. And multiply that by the area of the wing, get the lift. Okay. And of course, all this stuff was known back in the 1700s. It had all been worked out and measured. Bernoulli was a 1700s type guy. There were Bernoullis late 1700s, early 1800s, whole family of them. Okay. Got a pipe. And you got water flowing in the pipe. Okay. This is open to the air. So maybe easier if we just think of two place points inside the pipe. Okay, let's start with point A. Good way to do it. If you increase the velocity in the pipe, what happens to the pressure on the pipe? It goes down, right? Faster the water flows in the pipe, the greater the pressure. I mean, the less the pressure. Okay. Now let's say you have this pipe is pressurized. Okay. So let's just say maybe you even start out with zero velocity or small velocity, and you got some source of pressure over there, or maybe might be easier to think of the pipe as descending, and maybe you got a big reservoir up there or something. Okay. Well, if you have zero velocity here, then water is going to rise in this tube to come to the level of the water over here. Okay. If you start moving fluid through here, the pressure here drops. So if your water level at some velocity is here, then what's the water level if the fluid is moving faster? Does the water level go up or down? Water level at an increased V would be here. Okay. Now you can analyze that. The water in here isn't moving. And you kind of regard the water in here as a pressure gauge. And you got some pressure in this tube, some small V, water's going to be higher. At a greater V, water's going to be less because of the, well, because we're in this equation. You can work out the problems, okay? You can read your text and see how that's done. I'm going to give you a variety of examples. So I don't want to get too close because we really kind of got 3 points to worry about there. And I don't want to go into that detail. Okay, now you got a vertical section of pipe. It doesn't have to be vertical. I don't want to do that. And my picture be just easier to draw. Horizontal section of pipe with a little break in it, little hole there. You got water flowing in here. Or some fluid, could be oil, could be some kind of fluid. And out here you got air. If you got a big enough velocity in here, you could have negative pressure. In other words, I'm trying to make this a little more explicit. Might be clearer. You got a river, water flowing in the river. Okay. And you got this wall between the river and the lake. Now, there are other things to be considered, but let's just say the water level is pretty close to the same between the river and the lake. Which way is water going to flow? Is it going to flow out of the river toward the lake or from the lake toward the river? Okay, same from the lake toward the river. Now, both the river and the lake are exposed to the atmosphere, so at least at the surface, they're at equal pressures, right? And if their water levels are pretty much the same, then you don't have much pressure difference at any depth. So if this is a vertical break in the wall, pressure is the same. Well, the pressure away from the break is the same in both. So since you have velocity, higher velocity here, you've got lower pressure here. So water pressure from the lake will push water into the river. Make sense? So you can think of point A here and a point B here. Water depth is the same at both points, so that your y is constant. Since y is constant, your velocity and pressure have equal opposite. Yeah, that's easy. So now if you know the velocity in the lake, assume the velocity, if you know the velocity in the river, assume the velocity in the lake is 0, then you can figure it out. If you have the numbers, it's easy to use the equation. Okay. Trying to think of examples that'll help you with the problems I just posted. And you have circulation here. And if you know about hurricanes, I mean, I never been much, I don't know much about them. You know, you got the eye wall, and you got the eye, and you got circulation around here. Okay. What's faster, the air out here or the air in here?
Here.
Yeah, well, the air velocity at B is greater than the air velocity. What did I say? Air velocity at B is greater than the air velocity at A. If the altitude's the same, then it can declare the pressure is greater at A. So given enough information on a hurricane, like if you know how fast the air is moving out here in the outer rings, outer bands, and if you know the pressure in here, that tells you what the air velocity ought to be. Or if you know the air velocity, it predicts your pressure. Okay? So, the bad hurricanes have really low pressures. So, that makes sense. And it's all conservation of energy. I'm not going to talk about the PV thing right now, but I might talk about it a little bit in lab. Okay, actually, this is some variety of situations that'll get you started. Kind of similar to the situations you're going to see in the problems that I posted. Okay. And there are other things. You need to read the chapter to get some of the terminology. You know what gauge pressure is? And I'm not going to tell you. Okay. But I refer to gauge pressure in a couple words. It's very simple. All you got to do is read the chapter. It'll pop out at you. Okay. You don't even have to read it that thoroughly, but get the chapter into your head, because there are a lot of situations that I'm not taking the time to talk about. I'm talking about this stuff. Generally, toughest thing that you have in the chapter is the application of Bernoulli's equation. That's what I'm focused on. We've also talked about pressure and so forth. I guess I should talk briefly about buoyancy. But buoyancy is fairly easy once you understand pressure. I've got a cube or rectangular solid, and I'm holding it under water. Okay. You got a buoyant force on it. Why is there a buoyant force? Because the pressure on the underside is greater than the pressure on the upper side. Pressure on the sides is perpendicular to it, so it does nothing to the vertical force. Okay. If you got an irregular solid, well, you got a bunch of little area increments. And we get a better appreciation for that when we start doing surface stuff in multivariable calculus, which is kind of challenging in some cases. But for every upward facing increment, you got some downward facing increment. Okay. And no matter what the angles of these things are, well, I don't want to get into all the details. You analyze those increments. And you find that the net force under is greater than the net force above, which is kind of intuitively obvious, no matter what the shape of the object. And then it comes down to the buoyant force is just equal to the weight of the water that's displaced. For a rectangular object, it's easy to do that. Just give it some dimensions. A by B by C. Okay. And then these two dimensions down here give you the area of the bottom. These two dimensions give you the area of the top. And if you know how thick it is, you know what the difference in pressure is. So you write down the expressions for the pressure under and the pressure above, take the difference, and then calculate the volume of the thing multiplied by the density of water, and you're going to get the same thing. So for rectangular solid, it's easy. For an irregular solid, we wave our hands in physics because we're not assuming multivariable calculus. But once you've got multivariable calculus under your belt, you have this machinery to do it for any shape. Okay. So, and we might well do that. Well, that's buoyancy. And again, Archimedes' principle, which everybody should learn in middle school, and then actually had it reinforced somehow, but often doesn't happen. It's amazing. Tells you that the buoyant force in any submerged object is equal to the weight of the water it displaces. Okay. Okay, an example that actually starts going toward thermodynamics, but to help maybe convince that there's a relationship between the energy and PV. Okay. I've got a hand pump sprayer. It's a great example of a lot of things. Okay, I've got to do work on the air to compress it. Okay. So that tends to heat up the air. They got PV equals nRT, which you know from chemistry, and you can apply it. And it turns out that the change in PV is equal to the work that you need to do. Because change in P pretty much tells you the average force that you got to observe. And that's a little bit of a hand wave there. Have to do with diagrams and stuff, and we'll do that probably next week. The volume stays constant. Let's say you want to cool your house with that. Machinery. Okay, so what you do is you pump up the air. Okay, pump it up to high pressure, take it outside, let it cool off. Okay. Then bring it inside and spray all the air out. Or as much as go out. Okay. Are you aware that the air that comes out of a compressed gas is colder than it is inside? Okay, have you experienced that? I mean, you can take canned air and spray it on your hand, it feels cold. Okay, don't know, a lot of people have used that. If you've ever used a sprayer, you know, you just pump it up without any contents, you know, just pump it up with air in it and spray it, and you can feel that the air is cooler. So you spray the cooler air into the house, right? Okay. Then you take it outside, pump it up again. Let it cool to the temperature of the outside, bring it in the house. Okay. Now that's an inefficient air conditioner, could use muscular power. And you're changing the heat content of things, but to change the heat content of just about anything takes a lot of energy. So, you know, you then invent compressors that'll run off of electricity. So they'll compress the air and then let it expand through coils and exhaust the heat from the coils to the outside. That's an air conditioner or heat pump if you do it in reverse. Okay. If you exhaust the heat inside, then that's the heat pump. We'll talk about that. Just kind of relating a little bit of the PV thing. I can explain if I need more time in the head. Okay. So you ready to come to lab on Friday? Get this pressure stuff down because we're going to look at several examples. We're going to start relating it to heat. And it's related to heat through PV equals nRT, et cetera. And I assume you're familiar with PV equals nRT.